Welcome back to the next session. So this is Shwethakumari, Assistant Professor, Department of PG Studies and Research in Statistics, SDM College, PG Center, Ujjire. So now we'll discuss some of the results in PPSWR. So the result 1 is an estimator y hat PPS, which is equals to 1 by n summation I runs from 1 to small n, via I by Pi is an unbiased estimator of population total under PPSWR. So now the expression y hat PPS which they have given, we need to show them as an unbiased estimator of population total under PPSWR. So as this is the population total estimator, so that's why the cap has been given, and this is for the PPS, so that's why we have written it as PPS. Now we know that there are capital N number of observations are there in the population, and small y1 p1, small y2 p2 and so on, small yn pn denotes the observation and the probabilities corresponding to the unit selected in the sample. So small y1 means, so now from the population, in the population you will be having capital Y1, capital Y2 and so on up to capital Yn, out of which if suppose you have selected the 10th observation, so that will be the first observation in the sample. So that's why the Y10 in population will be considered as small y1 in your sample. So likewise it is y1, y2 and so on, small yn with their respective probabilities p1, p2 and so on, pn. Now yi by small pi. So that yi by small pi means what? Small y1 by p1, y2 by p2 and so on up to small yn by small y pn is an independently and identically distributed random variables, since each of the y observations are independent. So this ratio will be independent and identically distributed. So now to prove it is an unbiased estimator, so that we have to check with the expectation. If the expectation of the expression is equals to the population total, then that expression can be considered as an unbiased estimator. So we'll start with by taking one term from this expression, that is summation yi by pi. So expectation of yi by pi, so we know that to take the expectation of x is summation x into the probability of x. So here also we take the same. So summation x means what? Here yi by pi into its probability pi. So as this small yi by pi can any of the observations from the population, so that's why while taking the summation you have to take under 1 to capital N by considering the population units, that is capital yi upon capital pi. So here pi get cancels out, so left over with summation yi. So what is summation yi? It is the total of the observation. You are summing all the observations, so it is going to give us the total. Total is denoted by capital Y. So expectation yi by pi is y. So now we will consider our original expression, that is expectation y hat PPS, that is equals to expectation of the expression is 1 by n summation yi by pi, and 1 by n is the constant term, so we can take out of the expectation, and also as yi by pi are independent, we can take the summation also out of the expectation. So we got up with expectation of yi by pi. So here expectation of yi by pi we already got it, it is capital Y, it is capital Y. Now what about this summation? This summation becomes nothing is there of the sample over here, it is the constant term, so summation will become small n because it is summation over 1 to small n. So it will become n. N get cancels and left over with y. So expectation of y hat PPS is y. So we proved that y hat PPS is an unbiased estimator of y. So next we will move to the sampling variance of population total in PPSWR sampling. So this is an expression for that. So we are going to get it from the derivation. So let us consider variance of y hat PPS, that is equals to variance of what is y hat PPS, just substitute that expression. Now whatever variance of ax, when you take the a constant term out, it will be a square variance of x. So similarly 1 by n, when it goes to out of the variance, so it will be 1 upon n square variance summation yi by pi. And already I have mentioned yi by pi is an independent and identically distributed, so this summation can also go out of the summation variance. So summation variance of yi by pi. Now we know that variance of x equals to expectation of x square minus expectation of x whole square, or we can write variance of x equals to expectation x minus expectation x whole square. So I am considering the second one. So 1 by n square summation as it is. So variance has written in the expectation form. So now 1 upon, so variance of y hat PPS equals to 1 upon n square summation expectation yi by pi, and we know that expected yi by pi will be y. So we are going to replace that whole square, and now we are going to use the term that is result expectation x square is equals to summation x square into p of x. So that we will replace, so summation x square, it is the yi by pi minus y whole the square term, and into pi, it is by mistake it is written p, it is pi. And now, and also I have mentioned it is that it's yi by pi can be any value from the population. So here we have considered the capital Y's. And now we are using the a minus b whole square formula. So by using that we will expand it, a square plus b square minus 2ab, and now we are multiplying this pi inside. So it will be pi cancels, and left over with summation yi square by pi plus y square summation pi minus 2 times of y summation yi. So now what happens here, this summation doesn't have any sample value, so the summation becomes n get cancelled, left over with n, denominator n. So 1 upon n, and here we can observe summation pi means what, 1, and so y square and minus 2 times y, and summation yi is what, y. So y into y will be what, y square. So minus 2 times y square, and here y square. So it will become minus y square. So left over term is 1 upon n summation yi square by pi and minus y square. So this is what is the expression what we wanted. So variance of y hat PPS, which is equals to 1 by n summation yi square by pi minus y square, hence the result. So I hope all of you understood how we can get the variance terms through the derivations. Here I end up with this session. Thank you so much.